Hello and welcome to this Chemistry World webinar. I'm Mariana Kneppers, Chemistry World Science Media Producer. In today's webinar, we will be discussing a very important and timely topic, scientific integrity. Fraudulent activity in research is on the rise, from paper mills to falsified data. A recent study found that numbers of these problem papers is doubling every 18 months. It's a daunting statistic, but what can we do as scientists? Today's webinar will be discussing just that. Our speakers will be demonstrating ways to spot this fraudulent activity and report it through the right channels. Now on to some introductions. First, we will be hearing from Jack Wilkinson. Jack is a senior lecturer in the Centre for Biostatistics at the University of Manchester here in the UK. His research interests focus on health interventions, particularly in treatments of subfertility, such as assisted reproductive technologies. He also undertakes integrity investigations for scientific journals and publishers, leading the NIHR-funded Inspect SR project. This project has developed a tool for identifying problematic randomized controlled trials, including those subject to data fabrication or falsification. Now, the slides are provided for this portion of the webinar. There are lots of links and resources included within Jack's presentation. So if you'd like to download a copy, you can go to the materials tab, in the GoToWebinar window, where you can click to download that file. That's located just between the settings cog and the questions button. We will then hear from Rhys Richardson, a postdoctoral research fellow at the Kellogg School of Management in Northwestern University in the US. He has a broad research focus concerning the formation of collective knowledge, maintaining the integrity of the scientific literature, and systematic studies of industrialized academic and scientific fraud. He's one of the maintainers of the Collection of Open Science Integrity Guides, also known as COSIG, which is an open source resource for performing post-publication peer review. I'm going to go ahead and invite Jack to join me on screen. You can go ahead and turn on your camera and microphone, Jack. There he is. Great to see you.
Thank you. Thank you very much for that introduction. Okay, so hi everyone. So thanks very much for having me today. So I'm Jack Wilkinson, and I am very much an outsider here today, I think. So I come from the health research world. So I'm going to be giving you a bit of a perspective on the problem of fraudulent research and how it relates to the field of health. Before I do that, I have to start with a bit of a disclaimer. So I'm not accusing anyone of fraud or any other type of misconduct here today. So I might say that a study is problematic or untrustworthy, but we leave open the possibility that this is, it could be due to fraud or misconduct, or it could be due to honest but critical errors. And I recommend that you don't accuse anyone of fraud either, actually, okay? And just in terms of my declarations of interest, so I do sort of stats editing and stats review for various journals, and I also undertake misconduct investigations for various journals and publishers as well, and sometimes that work is paid. Okay, so with that out of the way, let me sort of motivate this a little bit. So let me give you an idea of the world in which I work, and let me give you a sense of the threat that fraudulent clinical trials face, okay? So in health, our best way of testing treatments, of testing health interventions, is to use a study design called a randomized controlled trial, okay, an RCT. And very briefly, that's where we take some people with a certain health condition and we randomly allocate them to either receive a treatment or to some sort of control group, okay? And we make a comparison between the groups to say whether or not the treatment is beneficial. And that's as I say, that's considered the gold standard for testing treatments, okay? Now, normally, what happens is that multiple RCTs are conducted comparing the same two treatments, okay? So I've got multiple RCTs here. And if people have done multiple RCTs, then it makes sense to consider the evidence holistically, right? It makes sense to look at all of the evidence together. We'll use that to make a conclusion about whether the treatment is safe and effective. And we do that using something called a systematic review, okay? So what happens in a systematic review? Well, first of all, we attempt to identify all of the trials that have been done, okay, looking at our treatment that we're interested in, all right? And then we critically appraise the methodology of those studies, okay? So I've just illustrated that using a traffic light system here, all right? So in my little figure, the first trial gets a green light, we think that was done well. The second one gets a red light, we don't think that was done well. Third one was middling, and the fourth one was done well, okay? So we're looking at the methodological quality of these studies, all right? And then finally, we take the results from all of those studies and we combine them using a statistical method called a meta-analysis, okay? Pull all of the results together and reach an overall conclusion about whether the treatment helps, harms, or does nothing at all, all right? And these systematic reviews are really influential, okay? They're seen as a gold standard, the highest standard of evidence we have, really. They influence clinical guidelines. So in the UK, NICE use these to make treatment recommendations. They're used by clinicians to decide how to treat patients. And I don't think it's an exaggeration to say that this is really like a cornerstone of evidence-based medicine, okay? But unfortunately, we've come to realize that there's a problem with this paradigm, okay? So let me illustrate that with an example. And the example I'm going to give you is ivermectin for COVID-19, okay? So there were some systematic reviews that suggested that ivermectin was hugely beneficial in COVID-19. It would greatly reduce the chance of dying from COVID, all right? And unsurprisingly, this was very widely covered in the media and on social media as well. And actually it was used by sort of anti-vaxxer groups to sort of say, look, we don't need vaccination, all right? We've got this miracle treatment. If you get COVID, you can take ivermectin, it will save your life, okay? And I put some of the claims that appeared on the screen here. Strength of evidence for ivermectin has this week been supercharged. The evidence clearly shows that ivermectin prevents and treats COVID, etc. Okay, so that looks good, but unfortunately, it turns out that there was a problem with some of the RCTs included in those reviews. Okay, so what I'm showing on the screen here is purportedly the data underlying one of these ivermectin RCTs, okay? And don't worry that you can't see the individual values, that's not important, but it's a standard data set where each row is supposedly a participant in this clinical trial, and each column is a variable or a piece of information, so sex, age, things like this, okay? What I'm going to do now is I am going to zoom in, okay? So this is a snapshot from that data set to make it a bit easier to see. And I'm just going to give you 10 seconds or so. Have a little look at this yourself, okay? And see if you can spot any problems with what I'm showing you here, okay? And I'll tell you the answer in a moment. It doesn't require any knowledge of what the variables mean, what the numbers mean. See if you can spot any problems with this, anything that looks unusual. Okay, I'll tell you the answer. If I add some color coding to this, there are repeated sequences here, right? And actually, if I return to the original spreadsheet and add some color coding here, we see lots of repetition, okay? So huge blocks of data have been repeated in this spreadsheet, and clearly this is not authentic. And one possible explanation is that this is a crude attempt at fabrication, right? So somebody's copied and pasted blocks of data into a spreadsheet to give the impression of having this large data set from a clinical trial, all right? Now, unfortunately, it turns out that there were similar problems with some of the other ivermectin RCTs. And actually, once we remove these problematic studies, we call them, from the systematic reviews, this impressive benefit of ivermectin disappeared, okay? We were left with complete uncertainty, basically, about whether it helps, harms, or does nothing at all. So what's gone wrong here, okay? What's gone wrong? This is the cornerstone of evidence-based medicine. What has happened? What's gone wrong? Well, let's recap the steps that I described, okay? Let's look once again at what happens in a systematic review with a critical eye. So first of all, I said that we attempt to identify all of the RCTs that have been done on this topic. But that means if there are any fake studies or problematic studies, they're going to be sucked up okay, and included in this systematic review. And then I said we assess methodological quality, but unfortunately, those assessments are predicated on the assumption that the trials are authentic, okay? The authenticity of the trials is not questioned. And that's a problem because many of these fake RCTs report good methods, all right? So they're not detected by these standard sort of critical appraisal methods that we have. And then finally, that means that these problematic studies are included in a meta-analysis and they contribute to the overall finding of a review. So maybe you can see how these systematic reviews might act as a pipeline for fake research to influence patient care, all right? Now that's not good, okay? And certainly this isn't just hypothetical, all right? So we see examples popping up in systematic reviews in lots of different clinical areas. So I've just put a few different examples from different clinical areas on the screen here. Vitamin K for prevention of fractures, ivermectin, I already described, psychological therapies for chronic pain. These are all examples of systematic reviews where there have been serious doubts about the authenticity of some of the eligible RCTs. Okay. Now there's an organization called Cochrane, okay? I'm not sure if you've heard of them, but Cochrane are the leading health systematic review developer, I would say, okay? And Cochrane said, okay, this is a problem. We have a problem here. And so they introduced this policy called the Policy for Managing Potentially Problematic Studies. And what that policy says is, do not include problematic studies in a systematic review. And I think we can all agree that's a good policy, but it prompts a further question. How are we supposed to identify these problematic studies in the first place? Well, one proposal is that we should just look to see whether or not the study has been retracted, okay? Can we just use retraction status to say whether or not a study is problematic? Well, unfortunately, the answer is no, okay? Because it typically takes a very long time for problematic studies to be retracted. And unfortunately, many are never retracted at all. So what I'm showing you here on the left is the outcome 5 years after reporting 172 problematic clinical trials from one research group, okay? And if you have a little look at the bar chart on the left, it varies by publisher, okay? But you can see that the overwhelming majority of these studies have not been retracted after 5 years, all right? So what this suggests is, unfortunately, we cannot rely on retraction status alone to tell us whether or not a study is trustworthy, okay? So what can we do? If we can't just use retraction status, how can we identify problematic research studies? Well, we partnered with Cochrane to answer this question, okay? So we undertook the Inspect SR project, and the aim of this project was to develop a tool to help people to identify these problematic RCTs, okay? And briefly, I'll tell you how we did it. So we started by assembling a long list of checks that could be performed in principle, okay? And then we applied all the checks on that list to lots of RCTs in lots of systematic reviews to learn a bit more about the feasibility and the impact of applying them, but also about how they might go wrong, right? How they might malfunction or be misinterpreted. And then we also entered all of these checks into what is known as a Delphi study. So this is a large study of experts to see which of these methods are supported by the expert community, okay? And then both of those strands of evidence fed into a series of consensus meetings where we decided which checks to include and how to operationalize them. So this gave us a draft version of the Inspect SR tool. And then we did lots of testing, we got lots of feedback, and we used that to refine it and to deliver the final version, okay? So we ended up with something that looks like this, all right? So we've got the Inspect SR tool, and this guides the user through a series of checks in 4 different domains, and it prompts the user to make a judgment about trustworthiness in relation to each one of those domains, and then this feeds into an overall study level judgment, okay? So let's have a look at how this works, all right? So this is another example, another systematic review, probiotic treatment for women with gestational diabetes. And I want us to just have a look at one of the RCTs in this review. So what I'm showing you here, this is called a forest plot, okay? And it's showing the results from the individual trials. Each one of those blue squares is the result from one of these clinical trials. And this top one is the results from the trial by Danush and colleagues. And it doesn't look unusual in terms of its result. And over here on the right, this is the sort of critical appraisal that I mentioned earlier, okay? So this is like the traffic light system, and in fact, there are a number of traffic lights for each trial. But what I'm saying here is, according to this quality assessment, this trial looks pretty good, all right? Greens, a couple of yellows, it's very much in line with the other trials in the review. But let's apply some of the checks, just a few of the checks from Inspect SR and see what we find out. And I'm really just trying to give you a sense of the variety of things we might check in a published paper here, okay? Okay, so the first thing we check is obvious, okay? So does the study have an associated retraction? And actually, if we look on the journal website, this clinical trial has been retracted, all right? So there's a notice there that says they've done an investigation, they were unable to confirm the integrity of the trial design, the conclusions are unreliable. Okay, fine. If we saw this, we could just stop, right? We wouldn't need to assess it any further. We shouldn't include it in a systematic review, all right? Now, importantly, this study wasn't retracted when the systematic review authors did their systematic review. So a question to ask is, would there have been any other signs that could have alerted us to problems, okay? Okay, next check. Does consideration of other studies from members of the research team highlight causes for concern? Well, here we recommend that people check the Retraction Watch database, okay, which stores retraction notices, okay? And if I do a search on the senior author on this paper, it returns 72 notices, okay? So these are expressions of concern or retractions on other papers by this author, all right? And if we look at these relate to data integrity issues. So if I saw that the senior author had this track record, that might be something of a red flag, okay? Okay, so our next domain, inspecting conduct, governance, and transparency, we ask, are there important inconsistencies between the publication and the registration documents? So in the clinical trial world, there's an expectation that you will register your clinical trial, and that should really be done prospectively, okay? So that gives us a chance to look at the registration documents to see if there are any problems, okay? Are there any inconsistencies between what it says on the registration page and what the author said in the paper, okay? Now, if we look at that, this one was registered retrospectively, which isn't good, but nonetheless, there are still various contradictions. So there are inconsistencies between the registration documents and what the author said in the published paper. So for example, the recruitment period completely differs, the description of the control arm completely differs between the paper and the registration page as well. And actually the authors later went back to try to change that, okay? They later changed it to match. And what I'm showing you on the bottom of the screen here is the description of the control arm being changed on the registration page, okay? So that's somewhat concerning. Inspecting text and figures, is there evidence of manipulation or duplication of figures? So actually this paper didn't have any figures, so I'm going to show you an example from another clinical trial instead. Okay, so this was from a published RCT. I want you to just look at this for a moment and see if you can spot anything that looks unusual. These are supposedly results from a placebo-controlled randomized controlled trial. And if you look at this for a moment, you may notice that it's just the same panel repeated 6 times with the labels changed, okay? So even though these are supposedly measures of 6 completely different things with different units, the data when plotted is identical. There's no way that this is authentic, okay? So this is concerning. Inspecting results in the study. So here we have checks of statistics and data. One check we perform, are the means and variances of integer data impossible? And I want you to have a look at the APGAR scores, the top 2 rows of this table. An APGAR score is a variable that only takes integer values, okay, 1, 2, 3, 4, etc. And it turns out that for integer variables, there are only a limited number of possible means and standard deviations that you can get for a given sample size, okay? And what I'm saying to you here is the values I've highlighted in red here are not possible. They cannot occur. And we look at this using methods called GRIM and GRIMMER, okay? Another check, are any outcome data, including estimated treatment effects, implausible? So now I'm going to tell you that the second trial in these plots here, that's another trial from the same group. And you can see that there's basically identical results in the two supposedly different trials from the same group. And the same is true for some of the other things they looked at that I've not shown here as well. Now, even though these are trials in the same population of the same treatment, it's really unlikely that you'll get the exact same sort of point estimates, if you like, in the different studies. We have too much noise in health, so that looks problematic as well. So just to summarize then, if we did apply just some of the checks from Inspect SR, would identify concerns in several domains, okay? Would have serious concerns about the trustworthiness of the study, and then we wouldn't want to include that in a systematic review. We wouldn't want to allow it to contribute to patient care, okay? So if it's of interest, this Inspect SR tool is now available. We've made like an editable template and a detailed guidance document that kind of has examples of all of the checks. I think that's really important to help people, because I know a lot of people are thinking about this for the first time. They're trying to do it for the first time. So we think it's important to give them examples to help. Let's think of some other challenges we might face. So just for a moment, can you spot any problems in this RCT data set? Don't worry that I've given names and dates of births here, because these people don't exist, all right? So they don't mind, okay? But if I draw your attention to the first two columns, perhaps, you may notice that there's no correspondence at all between name and sex, okay? So this was actually created by ChatGPT, all right? There's no correspondence at all between name and sex. I'm not showing you the full thing, but if we looked at the full data set, we'd see other problems. For example, there are people with 2 right eyes. There are people with different birthdays for each eye. One person has as many as 5 eyes, okay? So that would be easy to spot if we could see the underlying data, but unfortunately in health, we often don't see the underlying data, okay? And there's a real risk that people are going to use large language models to produce more ambitious and potentially more convincing forgeries, okay? If we can get hold of the raw data, that really increases our chance of detecting problems, okay? So it allows us to do a more thorough analysis. We can check, for example, can we reproduce the results in the paper from the data, all right? And we can perform simple data visualization to try and identify problems. And we're actually currently working on an extension to Inspect SR called Inspect IPD for when data are available. I've just got a few examples here of how this can be helpful. So in the first one, I just plot the age of the people in the data set. By doing so, I can easily see that there's some repetition here. The example on the right is from a nutrition study, and by plotting some of the variables against each other, in this case I plot carbohydrates against fats, I can see that in the data set they're perfectly correlated. That's just not plausible, okay? It implies that everyone consumes carbohydrate and fat in the same ratio. Of course, in reality, people's diets vary, okay? That's clearly not authentic, all right? So having the raw data allows us to see things such as this. Just to end then, so I think it's fair to say that in health, at least, we've done a good job at asking, is the evidence good? But we need to start getting used to asking a different question, is the evidence real? And I suppose a question for you to go away with today, you know, would it have occurred to you to question the authenticity of the evidence you read? When you're assessing trustworthiness or looking for integrity problems, I think it really is important to understand any method you use, okay? And so you should consult the guidance that exists. So I've mentioned Inspect SR, Reese is going to talk about COSIG as well. But I hope that this kind of skepticism will become the norm for all stakeholders, systematic review authors, peer reviewers, journals, and people who read papers as well. Okay, thank you very much, and I'll stop there. Thanks.
Cheers. Thanks so much, Jack. That was a really, really fascinating presentation, a really good demonstration of some of the things that, we do need to be looking out for as scientists. And I love the Far Side comic at the end, really illustrates the point. Now we're going to move on to Reese's presentation. Reese has popped up on screen. Hi there. We'll pass control over to you to share your presentation. Perfect. We can see that. Fantastic. Well, enjoy, everyone. I'll be back after Reese's presentation for the Q&A.
Okay, thank you very much for the introduction. Thank you all for being here. My name is Reese Richardson. I am a postdoc at Northwestern University, and I'm going to talk to you today about COSIG and give you some vignettes from this resource. But first, some motivation for why we created COSIG. So first of all, you've seen a lot of news recently about breaches of research integrity. We heard about these sorts of things happening in health from Jack. There's also been an explosion of problematic research related to computer science and material science. There's lots of fraud in research analyzing large public health data sets as well. And in fact, a lot of this fraud is created by organizations that are called paper mills. You may or may not be familiar with this term, but effectively, paper mills are organizations that fabricate fraudulent manuscripts at sale. So people can buy those manuscripts and put their name on them to pad their CVs, to increase their chances of promotion or hiring or tenure or what have you. So here are a couple of advertisements that I found online from paper mills. These sorts of advertisements are not hard to find at all. You just need to put yourself in the shoes of a researcher that really needs publications, and you can see them all the time. So on the left, we have a paper mill advertising that they can get your paper accepted automatically in a journal that is indexed by Web of Science or Scopus or PubMed. And on the right, we have actually specific titles of papers where you can buy authorship positions on these papers. And these show up all the time. And at the beginning of the talk, Mariana alluded to a recent study coming out about the explosion of fraudulent research. And I was actually the lead author on that study. And basically, the basis of that claim is that when you compare the number of scientific articles over time, it doubles about every 15 years, the annual output of all scientific articles. In this graph, the y-axis is in log scale, so you have 10, 100, 1,000, 10,000, etc. So the number of all scientific articles is on the top. And then you can see that the number of retracted articles is doubling about every 4 years, as well as the number of PubPeer commented articles. And we'll get to what PubPeer is in a second. But then we also collected from a number of sources a aggregate corpus of suspected paper mill products. And this is probably just the tip of the iceberg of what is actually out there in terms of what paper mills are producing. And that aggregate corpus we found to be doubling every year and a half. So there is a big motivation for us to find more of these problematic papers so that we can understand, one, how large this problem is, and two, also clean up the scientific literature. So the good news there is that anybody can take part in this. In fact, anybody can do post-publication peer review. And what post-publication peer review is looking at papers, be it in chemistry or computer science or mathematics, or in, let's say, systematic reviews and clinical trials like Jack was talking about, and doing a peer review of these and leaving your comments in a public place. So to that end, I'd like to introduce two resources that can help you with this. The first is a website called PubPeer. And indeed, Many retractions of problematic scientific articles are preceded by comments left on PubPeer. And PubPeer is also a platform where you can just leave a comment on an article for any reason, adding additional context, pointing out problems with the article, asking a question of the authors, etc. I myself have left thousands of PubPeer comments on articles, and anybody can use it. It is a really useful resource for navigating the scientific literature. And I really encourage you to check it out, read the ways that it's being used in the recently commented publications, and you can even install a browser extension that tells you when an article has existing PubPeer comments on it. And then the second resource is COSIG. COSIG is the collection of open science integrity guides. I am one of COSIG's maintainers, and basically we want this to be a one-stop shop for how to identify problems in scientific articles, how to report them to publishers, and overall how to do post-publication peer review. So COSIG is immense already. We launched it earlier this year, and it has 32 guides in it on a variety of different topics. It is constantly expanding, and it comes in one big PDF if you want to read it all at once, or you can read all of these different guides on a number of topics. So because this is Chemistry World, I wanted to give a few vignettes from COSIG that might arm people that work in chemistry or material science with very easy ways to spot problematic publications. And once you know what to look for, you start to see this stuff everywhere. If you want more information on any of these, you can find it in COSIG, but I'll just go over a few different vignettes right now. The first has to do with energy dispersive X-ray spectroscopy, or EDX. So the principle behind EDX, it is a chemical characterization technique where you bombard a sample with high energy electrons, like you would find in a scanning electron microscope, for instance, and then the elements in that sample emit X-rays at characteristic energies. These emission lines are well defined for every element on the periodic table. So you can then look at the spectrum of emission energies, and you can identify what elements are in that sample. So you can see that some of the peaks in this spectrum here are labeled for tungsten, some of them are labeled for copper, and then there is a peak for carbon and a peak for oxygen. So because these peaks are at well-defined energies, it makes it very easy to determine if somebody is actually making up their EDX, or at least when somebody is making up their EDX, there are some telltale signs that you can start to see what's going on. So this is a published EDX spectrum, and I want to stress that at first glance, there doesn't appear to be anything wrong here. And if you did not have the pre-existing knowledge of how EDX works, you might assume that this is entirely okay. This is what an EDX spectrum looks like. But there are some glaring problems that come up as soon as you start to interrogate the spectrum closely. The first is hydrogen will never, ever show up on an EDX spectrum. It is too light an element to actually have characteristic X-rays, so it's never going to show up. So the fact that hydrogen is on the spectrum is already a problem. Another is that carbon and oxygen will only ever produce one peak. Again, these are very light elements. So heavier elements will produce multiple peaks, but you can see that there are multiple carbon and oxygen peaks, and carbon and oxygen each only have one peak. So the fact that there are multiple peaks here is a problem. And then finally, if you look at where those one peaks should be, carbon's single peak should be around 270 electron volts. And here you can see that it appears at 1,000 electron volts. And that is just not going to be possible. That's just not going to happen. So if you see a spectrum like this, you can go on PubPeer, you can post a picture of the spectrum, and you can clarify all of these different problems that show up. And you can even use the software DTSA2 to tell you where those peaks should actually be. So this is a very easy to use software that actually lets you simulate spectra and look at where different peaks are found. So if you were to post this on PubPeer, you could ask something like, could the authors share the raw data for the spectrum and clarify how they assigned the elements to these peaks? And you can also notify the journal that there's something wrong with the spectrum that you're seeing here. So EDX is often used to assay elemental composition. There are a number of different ways to do this, in short, you will often see these elemental composition tables in papers. And surprise, different elements have different masses. So an elemental contribution by atomic percent is going to be different than the composition by weight percent. So this is a composition table for water. So it's H2O, so you're going to have 2 hydrogens for every oxygen. But water is actually 88% oxygen by mass. And the good news about these elemental composition tables is you can check them all sorts of different ways. So you can say, does the elemental composition actually match what we expect or what the authors are claiming it is? So if they said that water was 80% hydrogen by weight, that would be a problem. And you can also check and see if the weight and atomic composition percentages are consistent with each other based on what we agree upon as the standard elemental masses. So this is one such chemical composition table derived from a energy dispersive X-ray spectroscopy spectrum. And that has its own problems, but we'll ignore it for now. And you can see that they've provided a weight percent column and an atomic percent column. And automatically, you should know that these weight and atomic percents are a little too close to each other to make sense. And in fact, when you check the claimed weight percent and recalculate the atomic percent, you can see that the percent by atom is completely off in the paper. So this is problematic in itself, and you might get on PubPeer and ask, how could the authors, could the authors clarify how they actually calculated these elemental abundances? This one is a little more high level. The principle behind the vertical line test is that certain types of data should be a mathematical function, i.e. there should be one value of y for every value of x. So for instance, if you were plotting your height or the height of a tree over time, you would expect there to be a single height at a single time point because that's how height works. And if your graph looked instead like this, where it seems to backtrack on itself, that doesn't make sense at all for the type of data that's being described. And the way that we can test if this is a mathematical function is we can look and see if there is a vertical line that we can draw on the graph that intersects this trace multiple times. And if there is, it might not make a lot of sense. So if you're a chemist, you're probably very familiar with FTIR, and that's what we're looking at here. This is an actual published FTIR spectrum, except you can see that it does not pass the vertical line test. There are parts of this spectrum that overlap on top of each other and seem to backtrack, whereas for every wave number, we should have a single value for transmittance. Here is another spectrum that has the exact same problem, where there are parts of the spectrum that seem to fall back on one another unexpectedly. And here's one that I don't even have to annotate because you can tell that this has just been hand-drawn. And again, this is something that has been published. So you can look for these sorts of things in all sorts of different data, basically anything that can be described as a spectrum or any type of data where each X value should correspond to a single Y value is fair game. There are some things that don't apply, but you can read about what those are in COSIG. And this is a remarkably easy way to spot data that has probably been fabricated. So again, like the best thing to do in this case is to make your observations public, because otherwise this remains in the scientific literature unannotated. So you can go on PubPeer and you can say, this seems to violate the vertical line rule. Could the authors provide the raw data? I'll stress that point that Jack made earlier, that if you can inspect the raw data, it makes it much easier to rule out if something actually went wrong in the preparation of this data set. And to that end, we can look for unexpected duplications in a data set. So this is, these are 10 different X-ray diffraction patterns that were collected at Northwestern University on the same sample, a quartz capillary tube, and they were collected on the same sample, on the same instrument, one after another with the same settings. What you should notice is that every single one of these patterns are unique. There is no data duplication between them because X-ray diffraction is a very noisy process. So you wouldn't expect these little fingerprints on these patterns to ever repeat. It is just incredibly unlikely to see that. But it is something that you see in the published literature all the time. So these are two X-ray diffraction patterns that were in a published paper. And you can actually see that despite the fact that these are different materials that they're describing, undoped in 1%, the X-ray diffraction patterns are identical down to the noise. So this could be a mistake. It could be that they posted the same pattern twice, or it could be that they didn't actually have the data. Either way, this merits a correction of the scientific record. And then you can see more extreme examples of this. So these are 4 different materials for which they're plotting the X-ray diffraction patterns. And you can see that each of these XRD patterns are identical to one another. It's the same spectrum 4 times. And this is in one paper, but actually this same pattern is used for up to 28 different materials across 8 different published papers. And again, like if you weren't looking closely, or if you didn't know about these other papers through a platform like PubPeer, you might read these papers and try to develop new work based off of them without knowing that they're probably entirely made up. Here is another example where you actually have internal duplications. It is not obvious until you spend a little bit of time looking, but actually, if you look at the tail end of these patterns, you can see that the same noise is being repeated over and over and over again. This is simply not possible. And it's likely that there are peaks that have been edited out here or what have you. And here is another example where you actually have a photocurrent response spectrum, but you can see that the noise is repeated exactly with each cycle of the spectrum, whereas you would expect a little more deviation each time. So again, you can ask the authors for raw data on PubPeer, but you can also alert other readers that these are the things that you observed so that they know what to look out for, and this could precipitate correction or retraction of the paper. So that's just a little flavoring of what is in COSIG. There's a lot more there across a variety of different topics, but I want to stress that COSIG is always evolving. And we're always looking for new material to add to COSIG, new ways to use COSIG. And to that end, there is an open invitation to contribute to COSIG. Here is just a few different people that have contributed to COSIG so far. And like I said, we have material on a lot of different topics, and we really want it to be as useful as possible for people that want to do post-publication peer review. And I hope to that I've convinced you that it's worth it to be one of those people. So you can always find COSIG at cosig.net. On the left there, we have our unofficial mascot that we're currently searching a name for. And if you have any questions or if you have a name suggestion for our mascot, you can send it to admin@cosig.net or at my email, which you can find in the chat. So thank you very much for listening.
Oh, thanks so much, Reese. Yeah, what an incredible presentation. I mean, I feel really empowered after watching both these presentations. But I also am just flabbergasted at what has been published. I mean, the hand-drawn graphs in particular, I just find really, really shocking because it looks like somebody's just scribbled some things and just published it. It is amazing what, people can just put out there,
Yeah.
Now, I'm going to go ahead and ask Jack to come and join us on screen. We'll do our Q&A session now. Lots of questions to ask, lots of things to cover. And I am going to start with this one here. One of the audience members is asking, how long does it take to perform some of these checks, like the Inspect SR guidelines or through some of the guides through COSIG? There's quite a few questions in this one, but how do we know when to apply these guidelines, when to spend that extra time, or should we be applying this across all studies we come across? Jack, I'm going to go ahead and start with you, and then we'll come to Reese afterwards.
Yeah, no, that's like an important question, right? So people are always worried about, obviously it takes time to do these checks, etc. One thing I'd say is, right, these systematic reviews, they are really influential, right? So I think it probably is worth taking a little bit of extra time to check that the studies that we're using to make healthcare decisions are in fact real. Now that said, we did some testing, right? And we got some user feedback, and the feedback we got is for first-time users, they reported a median of 45 minutes per trial. Now, I don't think that's too bad for first-time users. I expect that as people become a bit more familiar with that process, it may speed up. But, nonetheless, it's important to think about, can we improve efficiency there? Okay, how can we help people to speed that up a little bit? So actually, one area we're very interested in right now is, can we develop AI-assisted tools to assist with this type of assessment, not to do it for you. I think that would be a bad idea, but it might be possible to come up with AI tools that help. For example, they might be able to efficiently retrieve the relevant information, put it in front of a human reviewer, so the human reviewer has what they need to make the judgment. They don't have to go searching through lots of documents and stuff like that. They're my brief thoughts on that subject.
Yeah. Very good point. I wanted to follow up on the AI aspect of it, but first let's go to Reese. Reese, did you have any thoughts on that?
Yeah, so some of these checks are faster than others. So for instance, sometimes you can just see if something passes the smell test, or you can look and see like, oh, this has obviously been hand drawn, or this doesn't make any sense. But at some level, you're going to have to apply a level of expertise. That's what we hope to distribute with COSIG, is just tidbits of information that make it useful to see. It would take a lot of time to learn exactly how EDX works and how to operate in EDX and how to interpret and calculate elemental compositions, but it does not take a lot of time to say, hydrogen should never appear here. So there are certain things that are very easy, and there are certain circumstances that you should always be applying these checks, right? Like if you're going to build off of this work, or if you're going to cite something, or if you are going to include it in a systematic review. But if you're interested in just finding problematic papers, oftentimes there are hotspots that you can find in the literature where you can basically just quickly go through papers. You can spot these problems over and over and over again. So there are specific journals that come up all the time in my searches where I find problematic studies over and over again. There are also specific subject areas. So one of the big hotspots, especially in chemistry and material science, are these green synthesis articles, where it's green synthesis of nanoparticles for cancer treatments or for photovoltaics or something, to the extent where I feel like when I'm going through articles about green synthesis, every other article has something that implies that the article is just outright fabricated. And there are lots of different areas of the literature where this applies, but this is something that we need more people looking for so that we can better understand where these problematic articles are concentrated. But yeah, that's my.
Yeah, it's funny, and you do see trends across different research, and it's it's the kind of theme of greenwashing, right? People kind of glom onto, oh, green is the trendy thing, maybe that's what's going to get more clicks, more views, more reads, whatever. Now, going back to the kind of artificial intelligence angle of things, we have a question here from Mike who says, as language learning models and artificial intelligence are no doubt able to be trained on PubPeer and CoSig, how do you both feel that we can keep ahead of the curve as the paper mills will no doubt be able to use those kind of tools to develop more realistic fake papers?
Yeah, sure. So
yeah, go ahead.
Yeah, that was one big consideration that we had when we were developing CoSig is, are we giving people better tools to fake things? And there are a few different ways that we countered this. The first is that we're clearly not catching the majority of things that are out there, the vast majority of things. We estimate that only 10 or 20% of suspected paper mill products will ever be retracted. And we know that there is a large body of literature out there that is just, they're never going to see any actual consequences for fabricating this research. So in terms of a selective pressure to adapt, there really isn't one at this point. We hope to get to a point where there is enough of a impetus to change practices, but really what we'll need is a complete overhaul of the research incentive system. To that end, the point of fabricating papers is to save time. It is very costly time-wise and financially to actually conduct research and to go through genuine peer review, whereas it's very, very efficient to just slap things together in the shape of a paper to fabricate the peer review or to work with a compromised editor or to submit your work to a journal where you know it's going to be accepted no matter what, and get it published. And every additional check that it takes to fabricate something well, that takes time away from it, away from the process of actually publishing papers. So we think that, again, there's like no real incentive to adhere to these good practices if this is being followed. So I hope that that touches on it a little bit.
Yeah, Jack, did you have anything to add for those points?
No, absolutely. I mean, some version of this is probably the question I get asked most often. And I'm kind of working in a slightly different world to Reese, so that most of the fake clinical trials, I think, aren't being produced by paper mills. They appear to be being produced by lone clinicians or teams of clinical researchers and stuff like this. And I think it's fair to say that most of these people have fabricated these trials under the very reasonable assumption that no one is going to check or even consider the possibility that the study in front of them might be fake. Okay, so we hope by raising awareness of this issue and having people routinely check papers for fabrication, basically, I kind of think that might act as a deterrent, you know? So, say, for example, there's someone, heaven forbid, on this call today who's been fabricating their research and they've heard about now everyone's paying a lot of attention to it. I don't know, maybe I'm naive, but I don't think that person's going to go away and think, I need to do a better job of fabricating my data in future, right? Hopefully it's going to some extent act as a deterrent. But it is an important question, right? And, there is a concern that people will start using LLMs to make more convincing forgeries. Right now, we're doing some work where we are trying to fabricate data sets and trying to see if we can pick them up. So, it is still an important issue.
Yeah, we have Paul is asking, how are these publications getting through peer review in the first place? You know, reviewers should be spotting this. I think that's a really reasonable question. You know, you do have the peer review process in place, but how are these things getting through?
I can take that.
You want to go ahead? Oh, yeah.
Sure.
Go on, Reese.
So first off, when peer review does happen genuinely, it is a very porous process. We have lots of examples of fraudulent papers that are published in very rigorous journals, or have received a lot of scrutiny during peer review, and yet they didn't catch very obvious things. Again, like hindsight is 20/20, right? So when it does happen, there are things that can slip through the peer review process. However, we're also in the midst of a crisis where the number of scientific papers is growing exponentially, and the number of people that are reviewing scientific papers is not. It's growing sub-exponentially, and as a result, reviewer resources are getting spread thinner and thinner and thinner. There is probably less genuine peer review actually happening as author or as editors decide to default to fewer peer reviewers on articles. There is also the issue of systematic manipulation. So we know that paper mills will routinely provide fake reviewer identities. They will also bribe editors to accept papers at journals. So these are all routes by which these things can happen. You can invite people that you know will not genuinely peer review your article. And yeah, these are all mechanisms by which what's supposed to be a veracity checking process can be circumvented. And you can also, publish in journals that are just going to publish whatever you send to them, regardless of what the peer reviewers say, which in a profit-based publication system, that's sort of the behavior that gets incentivized. So there are lots of different ways that peer review can fail to catch these things.
Yeah. Jack, do you have any follow-up on that?
Yeah, sure. I mean, with regard to fake clinical trials in particular, again, they're not paper mill products. They're usually someone spent a bit of time trying to make a fake paper. And actually, a lot of those look superficially okay. As I mentioned in my talk, they often describe like good methods and stuff like this. So, and the other problem is, this problem, as I mentioned before, just hasn't occurred to peer reviewers, right? It just hasn't occurred that the clinical trial they might be reviewing might never have taken place, So if we just put this on people's radar, give them some suggestions of things they might look for that might indicate some problems, where you might spot some subtle contradictions and things like this, the hope is that will improve the situation.
Yeah, we've also had quite a few questions about the impact on either policy decisions, medical frameworks, things like this when it comes to these fraudulent studies. One of the questions we have is, given the impact that these fraudulent publications could have on the public, is there a push to make the legal consequences more significant? Do you want to go ahead with that, Jack?
I don't really know where that's going to come from. So we also say it would be a nice idea if there were more sort of consequences, but in the UK at least, right? Certainly it's quite rare for people to face legal consequences. I mean, Reese, I think, you can sort of advise a bit more on the situation in the US, but my understanding is the Office of Research Integrity actually investigates a very small number of cases altogether, but maybe you can give a bit more of a view on that situation.
Yeah.
Reese.
Yeah, so in the US, there are tens of thousands of people that receive funding from the Public Health Service, but the Office of Research Integrity of the Public Health Service only sanctions around 10 people a year. And in the last few years, it's been far fewer than that. Moreover, when it comes to actually, prosecuting somebody for something, if there is a legal framework that exists, then that framework needs to be applied very carefully on an individual level, and that is just not scalable. Whereas creating problematic papers and publishing fraudulent papers at scale is very scalable. And we highlighted in our recent paper a few different operations that demonstrate this, that this is something that you can grow very rapidly. So in short, around the world, there are very few places where there actually are legal frameworks for prosecuting this from a legal end. And I sort of balk at the idea that this should be our default method for doing these things, because again, it's just an issue of proportionality, of can the punitive measures actually keep up with the behavior that they are trying to disincentivize.
Yeah, I mean, as you said in your presentation, Reese, it is so difficult to even quantify how much of this fraudulent behavior is going on, because it is increasing so quickly over the years. So I think that is a really, really good point when it comes to the scalability of it. How do you police this? And then it comes across global laws as well. I mean, what one country does might be different than another country. And how do you judge where somebody's publishing from something else? It becomes quite a big kind of issue to tackle. Yeah, definitely a lot to think of there. I hate to say it, but we are at our time. This has been a really, really interesting discussion, though. Thank you so much for both taking the time to be here. A massive thank you to my wonderful Chemistry World team as well, Ben Vassler and Chris Pink, who've been working behind the scenes to make sure the event runs smoothly. Thank you all for joining us, and we hope to see you in another Chemistry World webinar soon. I'm Mariana Kneppers, Chemistry World Science Media Producer. Goodbye, and see you next time.
Thanks.
Thank you.
Thanks all.